Hey guys, my iPad is dead and I can't find my charger, so I'm gonna have to do this the old-fashioned way. But I am gonna make a quick video for you guys about the lac operon and stuff because a lot of you guys struggle with it and you guys asked me to do a video and I promised to get it out on Thursday, and I'm sorry, I was really busy over the weekend, but I'm not anymore. Okay, so I'm gonna start by defining a few things. So when we're talking about any operon, we have the DNA part, transcription factors, and we have the small molecules. So the important part about this distinction is that the small molecules only interact with the transcription factors and the transcription factors only interact with the DNA. Why is this important? If we talk about the lac operon, for example, I know a lot of people have a misconception that they say that lactose will interact with the DNA. That is not what happens. Lactose would be a small molecule and it will only interact with either an activator or a repressor. It will not interact with the DNA. So what could these be? Let me get a dark color. Okay, so for the DNA aspect, we will only be talking about promoters. So the transcription factors, regardless of which one they are, they will bind to promoters. The transcription factors, they can either be activators or they can be repressors. And these are important. So for the purposes of this review, I'm going to be drawing repressors like this and activators like this. Because the way that I want you guys to think about repressors is that they bind to the promoter to prevent RNA polymerase from reaching it, and activators push RNA polymerase. So I like how it looks like it fits a little bit over here. So yeah. And for the small molecules, we will either have inducers or co-repressors. And I've colored them the same way that I've colored these because I want you guys to understand that a molecule is called an inducer because it induces DNA expression, not because it induces a transcription factor. What do I mean by that? Inducers will either turn on activators or off repressors. That's what inducers do. They're not called inducers because they always turn something on. They're called inducers because what they induce is the DNA expression. They want you to make more protein. Co-repressors are called co-repressors because they will turn repressors on. So take these notes, review these. Now that we got that out of the way, I'm gonna actually get to talking about the operons and stuff like that. So turning the page, I am going to start talking about the lac operon, and then we're going to talk about arabinose, and then we're going to talk about RSC and mutations and stuff like that. So for any operon, the most important parts is that you're always going to have in your strand or DNA, you're going to have a promoter, and this promoter is going to be connected to a few genes. In the case of the lac operon, it's lac Y, Z, and A. A like I, like Y, Z, and I. But this right here is arbitrary. This doesn't matter. As like anything that has a promoter on it, as long as the promoter matches whatever transcription factor you want to use, this can be anything. But we have to know what lac Z and Y do, so I'm gonna write this down. So lac Z, lysis, again, I know that's not written with a Z, but it's just so you remember. And lac Y, I don't know. It allows lactose to come in. And then usually what you will see him do is like before this, he will put the gene for the actual repressor. So for this one is LAC-O, I'm pretty sure. And the reason why he put this before is that he wants you to understand that this is unrelated to the rest of this. This is its own thing. So before we talk about this whole thing, I want you guys to understand a thing about activators and repressors. If we have a gene that does not have an activator or a repressor, I want you guys to think about this gene as you in a car not pressing the brake or the accelerator. If you're in a car and you don't press the brake or the accelerator, what's gonna happen? You're gonna drive, but you're gonna drive in 1 mile per hour. So no pedal. You're not still, but you're also not driving at like 100 miles per hour, which I hope you guys don't do ever. But anyways, so the gene by itself would be no pedal. So if you just see this, that's a gene with no pedal. If we have the P-glow thing, if we didn't have a promoter and we didn't have any transcription factors happening, it would mean that all the time we would have a transcription of the genes that we want, but it would be very, very low. Activators would be like if you're pressing the gas, and repressors would be like you're pressing the brake. So if you think about it, it would be quite beneficial for you to brake stuff when you don't want to make it and gas stuff if you want to make it faster, which is again why we add transcription factors to our plasmids that we're studying so we can have the max amount of expression. So whenever you end up having a gene with now transcription factors, this is like not sensitive to whatever molecule we're talking about because of the fact that it's not going to have a gas that's controlled by the molecule or a brake that's controlled by the molecule. Does that make sense? I hope that makes sense. So not sensitive, it's usually going to be moderate to low expression. Now, if we have an activator, then we usually can get max expression, which is important that the activator and the repressor work. So lac operon is quite simple. Your repressor is LAC-O, and your activator is CAP. The inducer for LAC-O is low lactose. And the inducer for CAP is cyclic AMP, which we get in low glucose. Back to the gene again. We have the promoter over here. LAC-O, and then our genes. Y, Z, and I. So the questions that he will ask you will be pretty similar to the stuff that we ask in class. What if we have a mutation here? What if we have a mutation there? What will happen? What will be the effect on the production of the gene? So let's give you guys a starting example. Let's say we have a mutation here. Let's say the mutation makes it so that we have no LAC-O. I want you guys to pause the video and think about what happened. If you didn't have any LAC-O, then what would happen is you would not, in an environment where you don't have any lactose, you don't want to waste your energy making these things. Which is why you usually have the repressor in the promoter to prevent transcription. If you have no LAC-O, that means you don't have the repressor. If you don't have the repressor, that means that you're going to have you're always going to have low to moderate expression. Because there's no repressor. You don't need allolactose to turn off the repressor because there is none. So in your average environment, you're going to have some low to moderate expression. But, well, regardless of allolactose. But if you're in an environment that has low glucose, regardless of if the repressor is working or not, you're going to have the action of the activator because of the fact that you have low glucose. So if you have low glucose, you can have maximum expression. What you're not going to have is sensitivity to allolactose because allolactose will only interact with LAC-O, the repressor. And since there is no LAC-O, then you are going to have no sensitivity to lactose. Also, just to clarify, when I say low glucose, there's no like threshold of how much glucose there is. I'm just gonna use low glucose to say no glucose. Just to clarify any questions that you guys have, it just makes more sense to say high and low instead of high and no. So, a few more scenarios for you guys. What if promoter Y, Z, I, O. What if we have a frame shift mutation here in LAC-Y? Pause the video and think about it. I'm assuming you paused it, so I'm going to explain it. If you have a frame shift mutation, usually that means that you're not going to have a functional gene for this. Well, a lot of students ask me, does that mean that you're not going to have any expression of the other genes? No. This is because each gene after a promoter has its own, what's it called? It's not origin of replication. Reading frame. What the hell does this mean? We talk about codons a lot. Codons come in pair of threes. And if you mess one of them up, then all of your other codons, like if you add one over here, all of your other ones are going to be messed up, so you're not going to have the same protein. Like these two are going to be different and you're going to have some left over here. However, if this happens for LAC-Y, this is the reading frame of LAC-Y, which means that after this codon right here, you're not gonna mess up the reading frame of LAC-Z like you did when you added this. Because as soon as the ribosome sees this stop over here, assuming that the stop is not impacted, which he will tell you if it is or not, then the codons for here are still gonna work, regardless of how many bases you added beforehand. It's like, let's say we have 2 baskets and they're full of apples. If I put a rotten apple in this basket, which would be like adding a new base, it might make all of these rotten, but it's not gonna have any effect here. Does that make sense? I hope that makes sense. So anyways, if you have a frame shift mutation here, you are still going to have expression of this gene and this gene. So the lac operon is just gonna focus normally, and that is, you're going to have that repressor we talked about on the promoter, and kappa is also going to be functioning if you need it. Therefore, you will either have what that means is you have sensitivity to low lactose, which is something that we talked about, which is related to this. So if this is working, you have sensitivity to lactose, and you also have sensitivity to low glucose, which means that if you have allolactose, you're going to be repressed. Well, wait, if you have no allolactose, you're going to be repressed. But if you have allolactose, you're going to have expression. And if you don't have low glucose, then you're going to have, if you have glucose, that means you're going to have moderate to low expression, because you're not going to have the activator. But if glucose is low, that means the activator is going to be on, and you're going to have maximum expression. I hope that makes sense. So I want you guys to practice this on your own. Imagine, what if you have a mutation here? What if you have a mutation on the promoter? What if you have a mutation on, well, cap? I want you guys to think of these scenarios and practice in your head. I'm not going to give them all to you because I don't have the time. Now, I'm going to talk about arabinose. So with arabinose, it's similar. The only difference is that the repressor, I'm going to make it purple. Why? Because the repressor depends, the repressor's behavior depends on the amount of lactose, on not lactose, arabinose. So if you have no arabinose, it works as a repressor. But if you have arabinose, then it's going to work as an activator. But it's still the same molecule. So you have one repressor for the arabinose operon, but you have two activators because of the fact that you also have cap. So this is era C. So the only difference between this and the lactose operon is that for you to have max expression, you need both era C and cap to be working. So I want you to think about this and think of the mutations that we talked about. What would be the effect of a mutation? Again, promoter, you have B, A, and D, and you have the era C gene. What if the era C gene was broken? Well, if that means that no era C means no repression. If there's no era C, if there's no arabinose, I mean, which means that you're always going to have at least a low to moderate expression. But it also means they're going to have no activation. So even if you do have cap present, you are not going to get maximum expression. Because remember what I said, maximum expression is when you have your foot on the gas. And foot on the gas will mean you need all of the activators you can possibly get. So if cap alone gives you one arrow forward, that's like 2 times speed, and arrow C gives you another arrow forward that's also 2 times speed, that means that the maximum amount of expression that you get is 2 times speed times 2 times speed, which is collectively 4 times speed. If you don't have arabinose, you're only going to get 2 times speed. I mean, if you don't have era C, you're only going to have 2 times speed. Just like if cap stops working for some reason, you're also only going to be able to get 2 times speed from era C if arabinose is present. So I want you guys to think of these examples. I want you guys to approach this like this. Don't go straight to the answer choices. Think, what would the effect be on the expression itself? What would it be if you had arabinose? What if it would be if you didn't have arabinose? Now, I want to talk about P-glow, because that's something that a lot of people get confused with. It's very simple if you break it down. So in P-glow, you have a plasmid. In this plasmid, you will have ORI-C, which is the origin of replication. The only special thing about the origin of replication is that it has to match bacteria. So if I give you a plasmid that has the origin of replication for E. coli, you can only put it into E. coli. You cannot put it into another random cell. Then you have a promoter over here, and this one is PBAD, which just means that it corresponds to era C. Yeah, PBAD doesn't mean that whatever is following has to be era P, B, A, and D. It just means that it's going to interact with era C and cap. Then we have, whatever gene we want. Then right before PBAD, we are going to have the gene for era C, because we need to be able to produce era C. We don't need a gene for cap because most bacteria, if not all, have cap. So we don't bother putting it here, but we do need era C if we're going to use PBAD. And then finally, I'm running out of colors. You are going to have a gene for beta lactamase. So I'm going to talk about this first. The reason why you have the gene for beta lactamase is because, okay, I want you guys to think of it like this. I have a petri dish. The way that you insert these plasmids into the petri dishes, it will be like this. You will have a colony. Let's say this color is good. So I'll have a colony already here. And then I put my plasmid in. And then after I do whatever I need to do, your petri dish is still gonna look like this, but you're gonna have a few dots that are fluorescent. If you put this on the fluorescent, you're not gonna see anything because there are just so many bacteria in here that it's gonna block the fluorescence, because only like 2 out of the 20,000 bacteria in this plate got it. So what you do is you put a beta lactamase gene in here. So not only do they make GFP, they also make an antibiotic resistance mechanism, which means that instead of having this, we end up having a petri dish that we add like a antibiotic, and then we kill all of this, ending up with only the bacteria that we want, and then they can grow into bigger colonies. So yeah, now I'm gonna talk about this. I want you guys to think about this part of the plasmid as just that drawing that I had before. You have your promoter, your era C, and then instead of having B, A, and D, you just have the GFP, but I'm calling it glow. So, the way that you would practice P-glow problems is the same way that you practice all the other problems. What if you have a mutation here? What if you have a mutation here? What if you have a mutation here? How would that impact era C? How would that impact CAP? That's all that he wants you to do. Just think of this as just any other promoter. Okay, so I hope this was helpful. And I'm, again, so sorry that I came out with this so late. And if you guys have any problems, you can either, don't leave it in the comments actually. Email me on Canvas, please. And I will be studying for my physio exam until very late tonight, so I will probably be available to answer you. So yeah, good luck on the exam.